We are very pleased to welcome Andrew Gordon Wilson today to present his work on how do we build models that learn and generalize. Andrew is faculty at the Courant Institute and Center for Data Science at NYU. Prior to that, he held positions as assistant professor at Cornell University, research fellow in the machine learning group at Carnegie Mellon, and did his PhD at the University of Cambridge here in the UK. Interests in probabilistic modeling, scientific computing, Gaussian processes, Bayesian statistics, loss surfaces, and generalization. Andrew, welcome to Oatmeal.
Thanks so much. It's really great to be here. I overlapped a bit with Doran Gall when I was doing my PhD at Cambridge, and it's been very interesting to see all the great work and exciting things that people have been doing, and really fun kind of to each have our own groups and to be collaborating again. And working towards similar sorts of research ambitions, and it's been exciting to see the amount of progress really that has happened in the last 10 years. And part of this talk, even though I've titled it Bayesian Deep Learning in a Probabilistic Perspective Generalization, is what I would tell myself if I could go back in time maybe 10 years and save myself a little bit of trouble thinking about things the hard way and sort of maybe hitting a few major roadblocks. And I guess with that, I'll also start with just an announcement. So I do have some postdoc openings in my group. So if any of you are near graduation or would be interested in doing a research visit or something like this, feel free to reach out at some point after the talk. I've listed some topics of interest, but generally we're just hoping to make big contributions to open questions in core machine learning. So this includes Bayesian deep learning, Gaussian processes, optimization in deep learning, generalization. We've lately been quite interested in physics-inspired machine learning, as well as learning symmetries, invariances, and equivariances, like to rotation, translation, scale, etc., automatically from the data, which is quite an interesting learning problem itself, and a way in which we need sometimes some kind of special procedure. Okay. So I'll start with a pattern recognition problem. We have some airline passenger numbers indexed by time. And I'd like you to take a vote. Which model would you choose to fit these data and make extrapolations into the future? Choice 1, choice 2, or choice 3? Feel free to just enter 1, 2, or 3 into the chat. Or if there's a fancy polling feature, we can use that as well.
Seems like we're getting a lot of ones right now.
Okay. I only see 6 votes. Okay, well, that's good. I mean, it's good in that it's bad, but it's good because I'm going to argue for something other than 1. If I argued for 1, then we wouldn't learn anything, I guess. So I think we should go with choice 3. And in fact, I think that choice 3 is probably insufficiently flexible. And the reasoning is there's going to be some ground truth solution that we're going to be able to get closer to through some setting of the parameters wj in choice 3 than could be possible in choices 1 or 2, which are just special cases of choice 3. And by the same logic, choice 3 is probably insufficient. And I guess people who go with choices 1 or 2 typically are worried about overfitting, for instance. I guess in practice, though, a lot of us are using something like choice 3. We're now quite commonly using neural nets with tens of millions of parameters to fit problems with tens of thousands of data points, like say CFAR10, which has 50,000 points, and finding we get very good generalization. If you work with Gaussian processes or various types of kernel methods, you're actually implicitly using models with an infinite number of parameters that are extremely flexible. These models are universal approximators, but often these models are also known to perform quite well, especially on problems with a small number of data points. Towards resolving this seeming contradiction, how we can sort of embrace a model that's super flexible and potentially not overfit and still see good generalization, it's helpful to think about function space perspectives. So here we have a distribution over linear functions, which has been induced by a distribution over parameters in a simple model W0 plus W1x. We can visualize this distribution by sampling from the distribution over W a bunch of times and just getting different straight lines with different slopes and intercepts. In this figure here, we have a conceptualization of all possible data sets on the horizontal axis and the marginal likelihood on the vertical axis, which is the probability that we would generate a data set if we were to randomly sample from the distribution over the parameters in our model, just like we were seeing in the last slide. So this blue curve here corresponds to the model we had on the last slide. It can't generate very many data sets, just straight lines with different slopes and intercepts. But because this is a proper normalizable probability density, it's going to have to give a lot of mass to those data sets. We could imagine another type of model, hypothetically, like a big MLP and a broad distribution over the parameters, which can generate a wide range of data sets, but it's spreading its support very thinly. It won't give any one of these data sets very much prior probability. We could alternatively imagine a different type of model in green here, which is quite flexible. It can support a wide range of different data sets, but it also has useful inductive biases, like say translation equivariance, the idea that if we translate an image, its class label remains unchanged, and that might describe a model like a convnet. So it has the flexibility, but it also distributes its mass carefully so as to allocate mass to the types of data sets that are representative of the problems that we're trying to solve with that model. On this slide, we additionally have three other figures which show how these models could behave as they're exposed to more data. So the green model has wide support, so it contains some good ground truth description of reality in its support. There's some setting of its parameters which will give us a good description of reality, but it also has reasonable inductive biases that allow it to contract efficiently around that description of the data. In blue, we see efficient contraction. The model gets very constrained very quickly by the data, but it becomes erroneously constrained and it contracts towards a bad solution. And then in the third panel here, we have the support. We cast a wide enough net to contain a good ground truth description of reality, but we have bad inductive biases, so we don't contract very efficiently around that solution. And so I would say it's very important not to conflate parameter counting with complexity. We can have models which have a lot of parameters that are in some sense very simple, and we'll see this a bit later when we talk about Gaussian processes. And also not to conflate sort of flexibility and complexity. So we can have also models that are very, very flexible and don't overfit because they have reasonable inductive biases. So we really shouldn't think of generalization from this one-dimensional perspective of how flexible is the model, how much support we have. It really depends on a lot of other things. And the inductive biases, the distribution of support will be very, very important. So I'm sure many of you are already sold on Bayesian deep learning, but briefly some points for and against. So as we've already started to discuss, it can be a good framework for thinking about model construction and understanding generalization. It's a natural way to represent uncertainty. I think this is a fairly well-known advantage, which is crucial for decision making. If we have to make a decision, a point prediction in many cases is useless. It's very helpful to have a distribution, and one might even argue that if we could never possibly imagine what we're doing ever influencing a decision, whether it'll ever have any practical importance or whether it should. Perhaps less well understood advantage is better point estimates. And this is something we'll focus on a bit in this talk. Because Bayesian neural nets can represent so many compelling and complementary explanations to a given problem corresponding to different settings of their parameters, doing this Bayesian model average is going to really improve not just our representation of predictive uncertainty, but also just the quality of our point estimates. And this is something I think that is, now starting to get recognized. It's starting to be realized, but it's taken quite a while to get there. You can sort of use Bayesian methods to interpretably incorporate prior knowledge and domain expertise. It's been very successful before. So neural nets have come and gone in popularity, and the last big wave of popularity near the end, Bayesian neural nets were achieving the best performance of any other approach. And so this tells us that there is sort of treasure buried in some direction, and we just need to sort of extract it using new tools, because these models have changed such that the methods that Radford Neal was using in the late 90s are no longer often that applicable. And as we've already started to discuss, a lot of what's been perceived as mysterious about neural nets actually can be quite natural when viewed through the lens of probability theory. Why not? I would say these points are almost becoming invalidated, but can be computationally intractable. Fundamentally, we're trying to compute a really high dimensional integral, but it doesn't necessarily have to be. There's been a lot of progress such that we can get at least approximate Bayesian procedures that don't take any longer in terms of training time than just standard SGD training, but do have better generalization performance and a reasonable representation of uncertainty in many cases. Can involve many moving parts. There are often more design decisions associated with using a Bayesian approach than just doing classical training, but we gain from thinking about these design decisions, and in many cases we can actually remove away a lot of the complexity. So sometimes there are only one or two things that we really need to preserve about a Bayesian approach to achieve good performance, and I think it's good to think critically about what really matters when we're trying to solve a practical problem, and there's been a lot of progress in that direction as well. In sort of a foundational sense, the predictive distribution that we want to compute typically is given by the sum and product rules here using a Bayesian approach, where we look at the conditional predictive distribution given our parameters and multiply by the posterior over our parameters given the data. So in words, what this equation is saying is don't just bet everything on one hypothesis, one setting of parameters, use every possible setting of parameters and weight them by their posterior probabilities. And as we mentioned, this can have particular advantages in deep learning. We can also, in this sense, view classical training as actually an approach to approximate Bayesian inference. And this isn't really a gratuitous sort of observation. It's actually quite helpful, practically speaking. So if we set our posterior distribution to a point mass centered around the maximum likelihood or regularized maximum likelihood map setting of parameters, and just substitute it into equation 3 here, we see that we recover our classical predictive distribution. And so this means that even if we can't come up with a good approximation to this integral, or computing this integral very accurately might be very difficult, that doesn't mean we can't do a lot better than classical training, even using ideas which we know will be wrong in a lot of ways. So for example, we know the posterior overweights in a neural network is highly non-Gaussian, but at the same time, a reasonable Gaussian approximation could be a lot better than just a point mass. And we're just trying to do better. And I think this is a very important observation. Also, typically, we're more interested in the induced distribution over functions than in parameters. And so, while it can be hard to think about how we should choose distributions over parameters, it's also hard to think about how we should do model specification in general. And these two things are very closely tied. So I'll argue that a lot of the properties of the prior that we would want in a Bayesian neural network are already hard-coded by the architecture design. And if I were thinking about how to develop new useful priors in Bayesian deep learning, my thought process wouldn't honestly be very different than thinking about how to do architecture design in general. I'd be thinking about things like translation equivariance, adding in various symmetries, thinking about learning symmetries, etc. And so this would honestly have very little to do in most cases with thinking about the details of some distribution over parameters in a neural network, which will have some effect, as we'll see, but the effect is not nearly as important as the architecture design. So I've long been interested in Bayesian machine learning. I became ironically interested in Bayesian deep learning after hearing a talk by Jorge Nosedal, one of the inventors of the LBFGS method at Cornell a few years ago, and he was arguing that SGD tended to provide better generalization than his batch BFGS methods for training neural nets because he hypothesized they converge to flatter regions of the training loss. And here, this is his figure. We have the training loss in black, the testing loss in dashed red. And we see that there's a horizontal shift between the training and test loss such that a flat solution will have still reasonably good test loss, but a sharp solution will have very bad test loss. Interestingly, I don't think the shift was explained very much when this figure was presented, but I think it's very intuitive. And I think there's a little bit of a trap where people associate it with something like distribution shift. We would expect this even if the training and test came from exactly the same distribution, unless our model was entirely specified by the set of training samples, which would be pretty unbelievable. If we added or removed a few points, we would hope that we would find at least a slightly different setting of our parameters. So we will often see this horizontal shift. There'll also be a vertical translation, of course. But if this was true and it meant something, and there have been some papers as well about how you can create flatness through reparameterization, et cetera. But I mean, for this to really mean something, and I think it does, the flat regions would have to contain settings of parameters which actually correspond to meaningfully different models. And if that's the case, then Bayesian integration, trying to basically integrate around a flip version of this curve, is going to be especially impactful, because that means we're essentially forming a very rich ensemble of good models that provide complementary explanations of the data. And so we should expect to see the biggest gains in those cases. So I've heard some discussions, more a few years ago now, thankfully, that maybe Bayesian methods are just not really meant for deep neural networks, and they're better for classical settings. I think exactly the opposite. That there's the most potential for applying Bayesian approaches in deep learning, because these models are kind of underspecified by the data, meaning that the posteriors are fairly diffuse, and in regions where there's high posterior mass, the different settings of parameters actually give us compelling and different solutions to our problem. It's also more challenging than classical settings, but I don't think we should back away from a challenge. And we're starting to see very good practical results from really trying to tackle this challenge of computing this integral more effectively. And towards that end, and partly inspired by that diagram I showed on the last slide, we started sort of from a sort of historical perspective in thinking about how we can just better understand the loss surfaces for training these neural nets, because if we could do that, then we could come up with better posterior approximations, better approximate inference procedures, better understand the potential utility of Bayesian approaches in deep learning, et cetera. And so one thing we observed that was quite surprising was that if you train a neural net twice with SGD, different initializations, doesn't even really have to have different initializations, but it can, and this will lead to more different solutions. Although those solutions have been perceived as isolated in the sense that if you try to walk from one solution to the other on a direct linear path, you'll incur very, very high loss, almost 100% training error along the way. There is a subspace along which these different solutions are connected such that you can walk from one to the other without really increasing the training loss very much at all along the way. And you can find these subspaces by basically first introducing a parameterized curve, like a quadratic Bezier curve or a polygonal chain, anchoring it to the two SGD solutions at the endpoints, and then learning the parameters of this curve by minimizing whatever loss you use to train the neural net, like cross entropy, uniformly, and expectation over the curve. So this looks something like a line integral across entropy normalized by arc length, which is actually fairly easy to optimize. And so when we do that, we find these subspaces where the different modes are actually connected. And here we have a few different visualizations. These are just two-dimensional slices through a really, really high-dimensional parameter space. And we can see that even in these slices, the loss surface is extraordinarily complex, which really suggests the question of whether it's a good idea to bet everything on a single solution, which is what we're doing with classical training. There are so many potentially good solutions. Now, another thing we noticed, which I'll actually describe a little bit more in a few minutes, was that these solutions weren't just connected in the loss surface, but the functions that we get by moving along these connecting paths and sort of associating different parameters along the path with different functions, we're actually providing very different types of predictions. So this wasn't just some kind of degeneracy in the model we had discovered. It was actually an empirical realization of that diagram I had a few slides ago. There are these flat regions, extraordinarily flat regions in the loss surface, and they do mean something. They do contain solutions which describe complementary and compelling explanations of the problem that we're trying to solve. So the next question is, how can we use this in some way to do better Bayesian marginalization, create a better approximation to this integral? And actually, the first observation in this direction was more specific to optimization. And so the idea is you start with a regular learning rate, and then you decay to a relatively high learning rate rather than to something close to zero. And this is a relatively high constant learning rate. And then you just basically collect the different SGD iterates, the different weights that we're traversing, and compute a running average, and then use that as your solution rather than the SGD converged solution. And so that procedure is called stochastic weight averaging. And the intuition is that when we're within a region of good solutions, and then we have this high constant learning rate, we're basically spinning around this loss valley. So there'll be a bunch of different points that are close together that all have very low values of the loss. And so when we use a standard optimization procedure, what happens is we basically converge to the periphery of this set. Maybe we move inside a little bit more if we're using SGD than BFGS, but honestly, we're still really very much on the periphery. And so by increasing the learning rate, we get to kind of spin around this set. And then by averaging the iterates, we get to move inside to a centered solution, which will be very flat and will lead to significantly better generalization. And so this approach is now natively, it's one of a handful of optimization procedures which are natively supported in PyTorch 1.6. Using it is just as easy as using optim.swa instead of optim.sgd. And I'd really encourage you to try it out, because basically you'll get better generalization for free and better calibration and so on. But in that direction, we can do even more. So rather than just computing the first moment, the next natural idea is, well, could we compute some kind of approximate covariance matrix when we're doing this sort of procedure where we're spinning around this region of low loss? And so if we compute the mean and a low rank plus diagonal approximation of the covariance, which is just written down in this line here, and use that as an approximate Gaussian posterior, for our parameters and then sample from that approximate Gaussian posterior, we get an approximation to our predictive distribution, that integral that we are wanting to compute. And this is a really, really simple approach, which is why we called it a simple baseline for Bayesian uncertainty in deep learning, and why it can be expressed entirely on just this slide. And so we did that, um, we got fairly good empirical performance, which I'll describe shortly, but we also wanted to sort of double check that this was something reasonable to do. So there is theory suggesting that if you run SGD with certain learning rate schedules, that asymptotically you are sampling from a Gaussian distribution centered on one of the local optima. But that theory makes assumptions which don't entirely hold in deep learning. And so we wanted to visualize basically how well this WAG procedure was capturing the shape of the posterior. And to do that, we created a subspace formed from the principal components of the SGD iterates that we were using in this WAG procedure and visualize the loss surface in that subspace. So this is actually very similar to the fancy visualizations I showed a bit earlier. And we saw that where basically each point corresponds to an affine composition of 3 high-dimensional weight vectors, and the color is the loss evaluated at that composition. And we see that basically that SWAG is doing a fairly good job of capturing the shape of the posterior in this subspace, which will be a fairly meaningful subspace. It'll capture a lot of functional variability. Okay, so empirically, here we're testing calibration. So on the vertical axis, we have confidence minus accuracy. Confidence is the highest softmax output we have in our classifier, and accuracy is the accuracy of using the associated class label. And then we've binned a bunch of different confidence levels on the horizontal axis. So a perfectly calibrated model would be a horizontal curve on this plot. An overconfident model would be above the horizontal curve, and an underconfident model would be below. We have standard SGD training in green. We have this SWAG procedure, SWA Gaussian, in blue. And we see that it does really improve calibration. We have temperature scaling and other approaches as well based on dropout. We have this K-FAC Laplace approach, which is a fancy Laplace approximation in pink. And we can see that this provides good calibration. It also can scale to very large data sets. So this was actually potentially the first Bayesian deep learning method, which was scaling to ImageNet, or was demonstrated on ImageNet with a large modern architecture. And this is because it doesn't take actually any more training time than standard SGD. It takes a little bit more testing time, but we'll talk about that in a minute. We also looked at covariate shift problems. So we can see that all the models in the top right here are overconfident. SWAG is relatively less overconfident. But this was kind of an interesting problem because a lot of the non-Bayesian alternatives, like temperature scaling, rely very heavily on having some kind of validation set to tune some parameters, which is not really that feasible if we've got a problem with covariate shift. So Bayesian model averaging helps with calibration in a very intuitive way. Because we're representing an epistemic uncertainty, we would expect to be overconfident if we were erroneously assuming that we had perfectly specified our parameters and that they're now deterministic after doing SGD training. And so the fact that neural networks is actually, neural networks are miscalibrated is actually no surprise from a Bayesian perspective. For that reason, we sort of understand, why Bayesian methods can help in this context. And with many of the alternatives, like temperature scaling, even though they can help, it's a bit surprising that they help, which can be a bit of a red flag. Basically, the idea is you just scale all the logits of a convnet by a single hyperparameter and learn that hyperparameter by cross-validation. It's a special case of Platt scaling. Works well on CFAR 10 and 100 and ImageNet, but we don't really know why, and we don't know whether it will work well on new types of problems. We have a reason to believe that Bayesian methods will help on new types of problems, and they don't require this kind of validation tuning, making them more immediately applicable to covariate shift problems. Okay, we can actually visualize epistemic uncertainty pretty naturally in the regression setting as well. As we move away from our data points, there'll be more different types of solutions which are consistent with our observations. That means our predictive distribution should spread out. And we do see this general sort of qualitative behavior in this WAG procedure, whereas when we compare it to just standard variational inference, we see that although the mean fit is kind of reasonable, the predictive distribution is a bit homogeneous. It's not doing as good a job at representing epistemic uncertainty. So when we were motivating this approach, we created that visualization of the loss surface in the subspace spanned by the principal components of the SGD iterates. And this led us naturally to wonder whether it would make sense to do inference directly in that subspace. So one of the biggest challenges in realizing a Bayesian procedure in deep learning is computing this extraordinarily high dimensional integral. If it's the case that a lot of the functional variability actually takes place in a low dimensional subspace, then we can make our life a lot easier. And so the idea is just construct a subspace and then do Bayesian inference in that subspace, and hopefully construct the subspace such that we're capturing reasonable functional variability. And so very simple procedure. Basically, we just parameterize our weights, W, for our neural net. So we just collect all the weights into one vector, and we write it as an offset, which could be the SWA solution in this case, represented by W hat, plus a linear projection of a very low dimensional vector of parameters, Z. And once we have this expression, we can write down our unnormalized posterior in terms of Z and just do basically any sampling procedure we like, because we're choosing to be in a very low dimensional space or variational inference or whatever we want. And then once we get those samples, we can basically convert them into W's using this expression here, W equals W hat plus PZ. So when we use the curve subspace that I presented earlier, we do see, in fact, here that as we move along this curve, we do get very different types of functions in purple that are all consistent with the data. And if I asked you, tell me which one of these functions is the right solution, you would probably have a hard time. And that's why probability theory says we should combine all these solutions together. And because they are different, we'll get a meaningfully different answer than if we just do maximum likelihood training. And we see actually that the predictive distribution here does have qualitatively desirable behavior. For example, it increases pretty significantly as we move away from the data and is somewhat reminiscent of the types of fits we get when we use a Gaussian process. So here we consider three different subspaces. The first is just a random projection subspace. So the P matrix that we're projecting with is just randomly sampled from a Gaussian distribution. And in fact, the mean fit isn't bad, but we can see the epistemic uncertainty isn't really great. It's pretty homogeneous. We can use a PCA subspace, which I would say is probably the most practical of these three options, where we basically create a matrix where each column is the iterate that we traverse minus the average of the iterates. And then we compute a partial SVD, and that gives us our P matrix. And this allows us to project into a very low dimensional space, like even a 5-dimensional space, and get predictive distributions that look this good, and actually quite good point predictions as well, as we'll see. There's also this curve subspace that we can use. So here we're actually looking at performance on CFAR 100. And we can see that there is a big improvement in point predictions. So with SGD, using a reasonable ResNet, we get 78.5%. Using the random subspace, we get 80%. Using the PCA, we get 80.5%. Using the curve subspace, we get 81.3%. So this is a pretty significant reduction in relative error, especially since the training time, especially for the PCA subspace, is not that different than for a classical SGD. And of course, the negative log likelihoods are also better, which is what we expect. But the point predictions are really non-trivially better as well. And I mean, this is using, with PCA, a 5-dimensional subspace. So we have like a wide ResNet with 30 million parameters, and we're doing Bayesian marginalization in this 5-dimensional subspace, which is capturing enough functional variability to see these non-trivial gains in performance. So marginalization is very helpful. Next question is, how can we do better marginalization? Now, the loss surfaces for Bayesian neural nets are very multimodal, and these different modes actually contain a lot of functional variabilities. So here we've got a sort of a cartoon depicting the multimodality. In the second row here, we have the predictive distribution. So the point we're trying to make in the second row of this figure is that the predictive distribution within a single basin has a little bit of variability, but not really that much. But between basins, there's actually a lot of variability. So that means if we want to just attack this really as an integration problem and not as a problem of how do we get good posterior samples from P of W given Y, then it's going to be super important to capture these different basins of attraction. And here in the bottom row, we have almost a Bayesian optimization-like figure, which is saying, supposing we've already evaluated our predictive distribution at these samples, given sort of in this mode over here, where should we go next in order to best improve our approximation of this integral? So you could think of this almost like an acquisition function. And of course, that will be to one of these other basins of attraction. So from this perspective, a method called deep ensembles, which has become quite popular, whereby we retrain our neural network a bunch of times with different initializations and then just ensemble the results, is actually a fairly compelling heuristic for computing the Bayesian predictive distribution, and will in fact give a better approximation than a lot of methods that we just accept without thinking as Bayesian procedures and deep learning, like single basin variational approximations. And so, in fact, we can do an experiment to sort of further suggest this point. So in the top panel here, we have this regression problem where we ran hundreds of HMC chains exhaustively and also evaluated some convergence diagnostics, et cetera, to form a predictive distribution. In the top right, we have the predictive distribution we get with deep ensembles. In the bottom left, we get the predictive distribution with single basin variational inference. And in the bottom right, we look at the difference in the Wasserstein difference distribution using the Wasserstein divergence between the predictive distribution we get with deep ensembles versus the stochastic variational inference procedure as a function of number of samples. And with deep ensembles, the number of samples is the number of models we've retrained. So we can see that this distance decreases very significantly as we increase samples with deep ensembles, but stays pretty flat actually with variational inference. So sampling from this approximate posterior with the single basin variational inference procedure isn't really improving our predictive distribution that much, or at least its difference with the exact predictive distribution. Now, this isn't really to say that deep ensembles is better than variational inference. This is more a comparison between single and multi-basin marginalization. So deep ensemble is a method that we often think about as non-Bayesian, is actually giving us a heuristic to compute a better approximation to the Bayesian predictive distribution than other procedures like single basin VI, which we kind of uncritically accept as Bayesian procedures. And so I think that we should really move away from like really myopically focusing on getting as good posterior samples as possible, and instead really think about what we're ultimately trying to do with those posterior samples. We want to compute an approximate Bayesian predictive distribution. And so if I told you, if I phrased this differently and said, you need to compute that integral, and you're only allowed to query your weight space at 5 different locations, I doubt many of us in this virtual room would say, well, I would choose the 5 locations given by 5 exact posterior samples from this distribution. Of course not. We could get very unlucky in doing that. We would want to choose these positions very carefully to try to capture the functional variability in our predictive distribution. And so we can improve on that deep ensembles procedure by also marginalizing within basins. That's what we do with multi-swag. It's basically multiple different swag approximations. We have a mixture of Gaussians, approximate posterior. And we find that this especially helps over deep ensembles when you have a small number of models or you have a lot of corruption in your data. And we also showed that it helps alleviate double descent, which connects actually in an interesting way to the opening example we had in this talk. So I said, which of those models would you choose? And I said, I would go with the 10,000th order polynomial. And really, if I could manage it, I would want an infinite order polynomial or even something more flexible. And so if we're using a reasonable Bayesian model, I would argue that we would expect performance to improve monotonically as we increase the flexibility of our model, because we believe the real world is a complicated place. And by honestly representing that belief, we should achieve better performance. And I mean, this is a point that's been made in various different contexts. In Radford Neal's PhD thesis, he has this nice example where he says, no matter how well we're doing, if we're considering a problem like character recognition, there's something else we can account for, like irregular ink blots or irregular writing styles or something that should improve performance just a little bit. And this is what we see when we look at this double descent example with multi-basin marginalization. So if you're not familiar with double descent, the idea is we start increasing the flexibility of our model and we improve performance up until a point, and then we start overfitting and performance gets worse, which is known as the classical regime. It's probably the type of thinking that influenced our votes on that question about which model to use at the beginning. But then something funny happens, seemingly, where we keep increasing flexibility and then performance starts to improve again. And so what we show here is that a good Bayesian model really shouldn't have double descent. We also see that there's a pretty significant performance gap between this multi-swag procedure and classical training. So we're seeing 45% test error here with this amount of label corruption on CFAR 100. With SGD training, we're getting below 30% error. So this is point predictions again. So that's pretty non-trivial as a difference. For a model which, in this case is a little bit more expensive, but it's still still a pretty big difference. So there was also another paper a few years ago called Understanding Deep Learning Requires Rethinking Generalization. And it showed that convolutional neural nets could fit CFAR with random labels and get 100% training accuracy. But of course, it could also generalize on the standard image recognition problem. And it suggested that this was in the face of everything that we know about generalization, because it showed that convolutional nets could greatly overfit the data, but in practice they weren't. Now, I would say that this result is actually completely natural from a probabilistic perspective and also isn't unique to neural nets and can be resolved by understanding this difference between flexibility or support and inductive biases. I would say we want flexibility. We want models which can fit noisy CFAR, but we also want inductive biases. We want to distribute our support such that our models are saying that those types of data sets are unlikely under our prior, though possible. And so we can demonstrate this behavior with a Gaussian process. So we see prior samples over our distribution over functions using a GP with an RBF kernel here. They all look pretty well behaved and simple. We see some data points in panel B here, and we fit that with our Gaussian process predictive distribution. All looks good. In panel C, we have a bunch of corrupted points, and we have our updated predictive distribution, which, without noise, perfectly runs through all of the data points. But, again, this is very different from the types of solutions that this model has a lot of support for, but it is contained somewhere in the support of the model. So to get something like the red curve in panel C, we would have to be drawing a lot of functions in panel A for a very, very, very long time. But somewhere there is some non-zero probability that we can generate that function. And if there's a strong enough likelihood signal, then our posterior will adapt to that and fit that function. And we can actually quantify how much our model wants to fit that type of data with the marginal likelihood. And we can compute the marginal likelihood of a Gaussian process, which, by the way, achieves 100% training accuracy on noisy CFAR10, just like the deep neural network in that paper. And we can see that the marginal likelihood decreases pretty significantly as we increase the number of altered labels. We can also do this for a Bayesian neural network and show that the marginal likelihood, the approximate marginal likelihood, decreases pretty significantly as we increase the number of altered labels. So there's been a lot of work in the last few years using Pac-Bayes to help us understand generalization in deep learning. Pac-Bayes provides explicit generalization bounds for stochastic networks with distributions over parameters, where loosely Q here is interpreted as a posterior, P as a prior, and the bounds are based on this expression here in equation 5 and number of data points. Non-vacuous bounds have been derived by exploiting flatness in Q, leading to the prediction that we get at least 80% generalization accuracy on binary MNIST. And I think this is an exciting result, and I think that Pac-Bayes is a very interesting research direction, especially in that it gives us quantifiable generalization bounds. I would say it's also very complementary and even different in some ways to, contrary in some ways to some of the things I've described. So Pac-Bayes does not tend to be very prescriptive about model construction or informative for understanding why a model generalizes. If we used this expression in equation 5 as a prescription for model construction, we would say, well, we want things like compact priors, and the papers that actually get better bounds use very compact priors, and we would want to strip away a lot of the dimensionality in our parameter space. It's going to be hard to have overlap between two really high dimensional distributions in our tail divergence, et cetera. But in practice, we actually see increasing the number of parameters over parameterization is very helpful for generalization. And this is aligned with the perspective that I've been describing. We want really large support to sort of cast a wide net. We should be careful about our inductive biases. Also, we've seen the pretty significant effect on generalization in doing multimodal marginalization. However, the generalization bounds in Pac-Bayes are not very improved by having a multimodal posterior. You just get a log factor. There's really not a significant difference. And we do see that a lot of the Pac-Bayes bounds in practice are doing parameter counting. They do depend on the number of parameters in a very sort of real way. Part of the reason that Pac-Bayes has not been too prescriptive about model construction could be because although some of the bounds are non-vacuous, they're still fairly loose. There are a lot of things we can do to improve the bounds, but not necessarily improve actual generalization. We had a different work which was relating posterior contraction of Bayesian neural networks to a quantity called the effective dimension of the Hessian. So the idea is you train your model, and then you compute the Hessian at your trained solution, and then you compute the eigenvalues of the Hessian. And the effective dimension is the sum of lambda I over lambda I plus alpha, where lambda I is the eigenvalue of the Hessian. And so we can interpret this as basically counting the number of sharp directions. Typically, when we look at the eigenspectrum of the Hessian, you'll see two prominent clusters, one with relatively large eigenvalues and one with essentially zero eigenvalues. And if we can sort of determine the number of eigenvalues in that larger cluster, we can find that it's actually a fairly good proxy for generalization. And when we compute this quantity for the double descent experiment, we see that in a region of low training loss, it actually tracks double descent very closely. And we can actually get some more understanding as to why this is the case and why this can help us explain double descent. So if we actually move around in the loss surface in the directions given by the eigenvectors with small eigenvalues of the Hessian, what we find is that there's almost no functional variability. And so this is saying, in other words, that it's possible to significantly compress these neural networks. This actually provides an explanation of why approaches like subspace inference that I presented earlier can work so well in practice, why it's possible to start with a 30 million dimensional neural net and reduce it to a 5-dimensional parameter space and capture a lot of the functional variability. Therefore, we can basically perceive two models with the same training loss but different effective dimensions as providing different levels of compression of the data. So from an information theory perspective, we can view models as providing compressed representations of training sets. And intuitively, the most compressed representation will capture the most regularity and provide the best generalization, as long as it has a similar amount of training loss. The reason that last caveat is important is because you could imagine that one way of getting low effective dimensionality would just be not to learn anything, in which case we'll probably also have pretty bad generalization. But in this interpolation regime, where we have basically zero training loss, we do track the generalization performance very well. And in fact, although the number of parameters is larger in these models to the right of the curve here, the effective dimension of these models is a lot smaller. And so the solutions are actually a lot simpler. And there's also some other intuition for why this is the case. So in a really high dimensional parameter space, flat solutions will occupy a much greater volume. And so they'll be more easily discoverable by procedures like SGDs. So in this sense, we could actually imagine that we have a blessing of dimensionality rather than a curse of dimensionality. And there's been an interesting paper by Tom Goldstein's group on arXiv for a while now called Understanding Generalization Through Visualizations. And I think this is actually a really nice paper, and it has a lot of nice intuitive observations like that. And so I'd recommend checking it out. It's actually quite a cool empirical exploration of generalization using visualizations. And it has a lot of other, I think, treasure buried in it. Like it does this experiment where it compares a bunch of different optimization procedures. It doesn't make a big fuss about it, but if you look at the figure, you'll notice that they all perform pretty similarly. Like BFGS, even Levenberg, Markar, and so on are getting essentially the same generalization performance as SGD on CFAR 10. Like maybe there's a very minute difference. And so I think there might be a bit of mythology about like the importance of SGD in achieving good generalization in deep learning. It's convenient in some ways, but it's not necessarily crucial. And these arguments around, for example, how flat solutions will occupy big volumes in high dimensional spaces explain why good solutions are still discoverable using something like BFGS. In this bottom row here, we also look at generalization as a function of width and depth of a network. A lot of theory papers lately have been focusing on width, like there are these ideas like neural tangent kernels where we look at infinite width, etc. But although this makes things easier to analyze theoretically, it's really depth that I think has made deep learning interesting and distinct in many ways from other types of models. It's depth, not necessarily that is providing flexibility, we can get that through width, but useful inductive biases for solving a lot of problems, hierarchical representations, etc. And so here we have level curves of a constant number of parameters in yellow, and we can see that these level curves correspond very loosely to improved generalization. In above the green partition, we have models with low or essentially zero training loss, and we can see that effective dimension does correlate very strongly to the test loss, but of course the train loss doesn't. We also have found that effective dimension provides significant improvements over relatively high performing generalization measures, Pac-Bayes flatness and things like this, and path norm, etc. And so it actually tends to work surprisingly well. And so as a final note, I'll also sort of briefly mention Gaussian process approaches to Bayesian deep learning. We talked about Gaussian processes when we were thinking about how we could resolve those results in that rethinking generalization paper from a Bayesian perspective. There are sort of interesting methods. I won't spend too long talking about them, but methods like deep kernel learning, which also leverage the structural properties and inductive biases of deep neural networks in combination with the non-parametric flexibility of a Gaussian process to achieve pretty strong predictive distributions in a lot of settings, especially in regression settings, and through something like the base kernel, capture notions of sort of distance awareness and so on, which is starting to become kind of a trendy topic in Bayesian deep learning. The basic idea is you transform your inputs through a neural net, and then you apply a base kernel to those transformed inputs rather than the original inputs. And you can learn the transformation jointly through the marginal likelihood in an end-to-end procedure. And we could really think of this in some ways as the best of both worlds in using a kernel method or a neural net. I think an advantage that kernel methods give us is the ability to work with infinite basis representations. So use the infinite order polynomial in a sense, but with a finite amount of computation through a beautiful procedure called the kernel trick. Whereas neural nets, even though the story is often big data and big flexibility, actually give us very useful inductive biases through adaptive basis functions and a mechanism for metric learning, which in many ways is like kernel learning. I think training a neural net is a lot like learning a kernel. And so we can bring these two things together and have infinitely many adaptive basis functions with inductive biases given by neural nets and see that we can get better point predictions than the standalone neural nets and pretty reasonable predictive distributions in a lot of settings. So here, the Bayesian representation of uncertainty isn't coming through a distribution over parameters in the neural net. It's coming through the Gaussian process, this infinite dimensional distribution over functions. We could extend this model further to also put a distribution over the parameters and try to marginalize those if we liked. And a couple projects in my group that we're sort of very excited about that are a bit distinct from some of these topics, but also have some interesting connections. We've been very interested in incorporating different types of symmetries into neural nets and other types of models. So a lot of the most successful models are successful because they capture structure like translation equivariance that we do see quite often in high dimensional natural signals. But ConvNets just capture translation equivariance. We might wonder whether we want rotation, scale, intensity, shears, etc. And so we worked on an approach which would allow us to generalize convolutional nets for equivariance to Lie groups on arbitrary continuous data. So a wide range of different symmetry groups on a wide range of different data types. So we might want to consider molecules, for example, which have no canonical sort of orientation or coordinate system. This is where some of these symmetries are going to be quite valuable. We can also use these types of models on physical problems like predicting dynamics, where these symmetries will conserve physical laws like angular momentum, etc. And we might also wonder whether we can learn the symmetries. So in a sense, this is challenging. There have been a couple sort of papers coming out like, can we learn a convnet kind of thing? And the reason this is a bit challenging is because even though convnets work very well because they have these constraints, most learning objectives don't select for constraints. Maximum likelihood just wants maximum flexibility, etc. We recently released an approach appearing at NRIPS called Augurino, where the idea is basically you can imagine a bunch of different transformations which correspond to different potential invariances in the data. And as long as we don't sort of move into a regime of harmful transformations, our training loss will be fairly flat. So while the training loss won't necessarily favor invariance, it won't be hurt by invariance if our data actually does have something like translation invariance, at least not very much. And so what we can do is we can basically imagine sampling from a distribution over augmentations and trying to learn the parameters of this distribution and just having some gentle regularization that'll push us up to the maximum level of invariance. And in fact, the details of the regularization are not that important because the loss tends to be very flat up to the maximum sort of transformation that we can do, and then extremely sharp. And so whether we use a little bit of regularization or even quite a lot, we'll tend to find basically the correct level of invariance. And we can also get sort of partial invariances. Like for example, the digit 6 is a 6 until we rotated it such that it looks like a 9, et cetera. And so we want some amount of rotation invariance, but not complete rotation invariance. And this is a direction that I'm generally, very, very excited about, trying to sort of figure out how to discover sort of constraints automatically from the data without sort of special procedures like cross-validation, et cetera. So in conclusion, I think that neural nets are actually a very exciting area for Bayesian deep learning, and really really have seen a lot of exciting empirical progress in the last few years. There is still a lot of work to do. One thing I haven't sort of discussed too much yet is tempering. There was a paper recently about what are called cold posteriors, this idea that if we raise our likelihood to a certain power, that's a power much less than 1, so 1 over t, t is less than, or sorry, much greater than 1, power 1 over t, where t is much less than 1, we can achieve better performance. So there are a bunch of experiments in this paper, Bayesian deep learning and a probabilistic perspective of generalization, which understand those results. And so one of the results, and if we have time in the questions, I can open up the slides and the figures for that, was that in the cold posteriors paper, they noticed that if you have just a generic distribution over the parameters of a neural net, and then you sample from the induced distribution over functions, you see that one of the classes is basically being predicted for all of the different points in CFAR10. And then if we sample again, it's a different class, but it's being predicted for all of the points in CFAR10, et cetera. We show that this is actually just an artifact of very simple prior misspecification. So if you instead use the prior n0 alpha I instead of n0 I for your parameters, and you tune alpha, set it to what you would use for L2 regularization or tune it using cross-validation, then this effect goes away. And you basically get a high entropy sort of distribution when you look at different samples from the posterior. Another observation there is that even if you use the miscalibrated prior, the n0 I prior, and the reason this happens is basically a softmax just saturates, the signal variance is misspecified, and you form the predictive distribution, it's also flat. So this wouldn't actually hurt our predictions. A third observation is that if you observe even 100 data points with the misspecified prior, and then look at the posterior distribution, it collapses down again, such that you have samples from the posterior basically allocating an equal number of points to each class. And so this is reflective of misspecification, but it's very sort of easily fixable misspecification, and it's not necessarily very significant. So if you're used to working with Gaussian processes, this is sort of like saying if we choose an RBF kernel to fit our data and then multiply it by 10,000 and find that the signal variance is kind of off in our fit. What we'll notice, first of all, is that, of course, this is something that's very easy to tune. We could learn it through marginal likelihood or cross-validation, or just compute the signal variance of our regression data or whatever it is and use that as an initialization. And B, that if we observe some data points, the posterior of the GP will quickly contract in that region. Okay, so another observation was, well, is it troubling that we might use tempering? Like, let's suppose we fix that prior specification, and maybe we're still doing a bit of tempering. Is that a problem? I would argue no. It basically reflects the honest belief that our model isn't perfectly specified, and I think it would be irrational to do otherwise. I think, in a broad sense, Bayesian methods are about trying to honestly represent our beliefs, and that includes our beliefs about misspecification. And if we just look at this purely from the perspective of it being kind of a learning problem, it would be pretty shocking if t equals 1 were the optimal setting of that parameter. We might hope that it's close to t equals 1, but it would be pretty amazing if it were exactly t equals 1. We can also imagine situations in which our likelihood and our prior are perfectly specified, but tempering will still be practically useful given a finite number of samples. And so this is where this observation that it's important to think about what we're ultimately trying to do with the samples comes into play as well. So we can imagine a situation where we have, for example, a very high dimensional Gaussian distribution, and we want to estimate its mean from samples. We know that the mass of a high dimensional Gaussian distribution will be very concentrated on a thin shell of radius root d. So the norms of our samples will basically just be root d. And if we, in this case, use tempering, so we use a temperature less than 1, and we compute a finite number of samples, our estimate of the mean will be strictly better. And so I think that we should pretty much always use tempering as long as it's convenient. But there are cases where benefiting from tempering isn't even an indication of misspecification. And there are instances where what seems like misspecification, like this idea that the softmax saturates, et cetera, can be very easily corrected. Now, in this paper, we also look at trying to understand the prior over functions induced by a prior over parameters in a Bayesian neural net. Many of its properties are controlled by the architectural design, like translation equivariance. A good way of trying to understand these properties is to think from a Gaussian process perspective and compute things like empirical covariance functions. And so we went ahead and did that. The covariance function is going to be much more important for generalization performance, even if we aren't working with a Gaussian process, than things like the signal variance parameter in our prior over parameters. So the difference between an RBF and a Mathieu kernel will continue to have a pronounced effect on generalization, for instance, as we observe more data, whereas the difference between an RBF kernel with one signal variance versus another probably won't actually have that much of an effect. And when we do compute these empirical covariance functions, we find that the neural network priors are saying, well, okay, images that look similar to each other do have higher prior covariance than images that look different from each other, et cetera, which are the types of properties we would want. We also saw in that rethinking generalization sort of experiment that the marginal likelihood of our Bayesian neural net did assign much lower values to the noisy data sets than the noise-free data sets. It wants to represent CFAR10 more than it wants to represent noisy CFAR10. And there are also many, many other results suggesting that this prior specification is actually quite reasonable, like the deep image prior paper, which showed that we could just randomly initialize a convolutional neural net, basically draw from a broad distribution over its parameters, and create a model which was very useful for image denoising and all sorts of other problems in computer vision. We also saw in the rethinking generalization paper itself that if you randomly initialize a convnet and then process your CFAR10 data with that convnet to create sort of random features, and then apply like a basic kernel smoothing technique, its performance is dramatically improved. So it'll go from like, it'll improve by about 20 to 30% accuracy on CFAR10. And so all of this suggests that these are actually inducing very reasonable priors. And I think this is, intuitively what we would expect from the architecture. And we're seeing empirically that we do benefit a lot from doing Bayesian marginalization versus standard optimization, which is also, I think, very intuitive because these neural nets can capture a wide array of different solutions corresponding to their different parameters. And this is most when we want to do Bayesian integration versus optimization. All right, that's everything. Thank you.
Thank you very much, Andrew. I think we can open the floor to some questions right now. I think we have a few that have been asked. Maybe I'll start with Rinak. You had about 3 questions. I'm going to unmute your microphone, and if you want to start with one of those questions, please feel free to go ahead.
So I wanted to just go back to the very start of the talk where you sort of like give us a choice between these like 3 models and ask which would we pick. And I feel like the real Bayesian way of dealing with this would be I fit all my models to the data, I compute the marginal likelihood for all of them, and then I do like weighted Bayesian model averaging. So I just thought there's like a bit of a disconnect here between, okay, let's go with the overparameterized models versus doing like Bayesian model averaging. And I was just hoping you'd comment on this.
Right. So this is a great question. I was actually just going to open some pictures about tempering and prior class correlations and stuff like that. I actually unfortunately forgot to include them in this PDF. But in terms of that sort of hypothesis testing choice, by choosing the big model, you are including all the other models. They're just special cases in the Bayesian model average. So that's going to be better than sort of separately sort of computing marginal likelihoods for each of these models and trying to weight them. So there's an interesting result, and I think there's a lot of confusion over this question, even in the Bayesian community. So if you open Bishop, sort of a canonical textbook on essentially Bayesian machine learning, you'll see in chapter 3 an example where they're considering polynomials of different orders, and they put a spherical distribution over the coefficients, and then they compute the marginal likelihood and show this Occam's Hill kind of property, where I think in that case, the 6th order polynomial has the highest marginal likelihood. And this is presented as a good thing because it aligns with our classical intuitions that we don't want a model which will underfit or overfit. We want something that is sort of just right. But I would argue that this result is actually an artifact of a bad prior. We wouldn't really want a spherical Gaussian prior over the coefficients of something like a polynomial. That would be saying that we think that the higher order terms are just as responsible for explaining the variance of the data as the lower order terms, which is not really what we believe. And if we look at the induced distribution over functions, as we increase the size of the polynomial with that kind of prior, it's kind of obvious why the marginal likelihood is like, no, stop, like don't go above the 6th order model, because we're inducing a crazy distribution in function space. And there was actually quite an interesting paper by Carl Rasmussen and Zubin Garamani called Occam's razor, where they instead basically compute the marginal likelihood for these types of models using a prior that decays with model order. And you can even learn the decay from the marginal likelihood or try to integrate it away. And in that case, you see something like Occam's asymptote. Basically, the marginal likelihood is saying, use the biggest possible model that you can fit in memory. Because there, the distribution over functions with the large models is actually reasonable. And so this, again, I think touches on this idea of the difference between support and inductive biases. I think we want flexible models as long as the inductive biases are also reasonable. And if we use the big model, in the case of the opening example, the 10,000th order polynomial, then we don't need to worry about computing marginal likelihoods for the first model and the second model, et cetera, and finding some way of combining them under different priors. I think it's preferable just to use the big model, have a consistent prior, and then let the Bayesian model average combine all of these things together.
I sort of see that. The process still feels very different. So like, sure, I could, maybe my priors are wrong or whatever, but I'm still like, it seems like I'm still performing like a fundamentally like different operation. But like considering these as separate models, and then, you know, presumably I can set my priors appropriately. So I sort of don't understand like what's wrong about like the theory. Like, what's the reason I shouldn't be doing this sort of like process?
Right. Well, I mean, maybe there's a way you could do it such that they would be similar, but it would be very hard to achieve that in practice because we need to think of a prior specification for each of those models and then use that to compute the marginal likelihood. And so the marginal likelihood is being computed under the idea that basically the model class you've represented is well specified. And so if we go with a 3rd order polynomial and compute the marginal likelihood, we're kind of imagining that the data sets we're considering are represented by the support of that model. And that's going to be kind of erroneous. So I think that's why this is not really a procedure that I would support over just using the big model and then doing Bayesian model averaging. Perhaps you could achieve a similar kind of outcome if you were very careful about how you did your prior specification, but I think it would be kind of contrived and not something in practice that we would really want to do. Does that make sense?
Yeah, great. Cheers. Thank you.
Feel free to ping me if you have other questions. I mean, it's a really interesting sort of fundamental question. I think there's a lot of confusion about it. The fact that there's sort of a textbook example of Occam's Hill, which actually could be an artifact of a bad prior. I think also it's interesting. I gave a talk at a Gaussian process summer school, and there are a lot of people are already very enthused about the idea of Gaussian processes, but they're still voting mostly 1 and 2 when I present the question in the way I did at the beginning of this talk. So they're using models implicitly with an infinite number of parameters, and there's actually a very beautiful derivation of the RBF kernel where we start with these basis functions and then we just increase the number to infinity. We can see that this model will be a universal approximator from the derivation as well. Like we basically get a bunch of Gaussian bumps with different heights, they're all densely dispersed, etc. And we're sort of happy with that, but still somehow when we're presented with the question in the form of the beginning of this talk, we kind of worry and go back to this sort of classical way of thinking. So I think there is a lot of confusion about it, and hopefully this paper on Bayesian deep learning and sort of probabilistic perspectives on generalization will help sort of clarify some of these points. But I think in a way, there's kind of a double think that's happening where we're sort of using neural nets that have way more parameters than data and finding that we get good generalization as a consequence, but still kind of worrying at a higher level about the idea of using models with lots of parameters. And I think the same is true of Gaussian process models.
Cool. So I think we're going to go to David Schultz now, if he's still here.
Hello, can you hear me?
I hear you.
Oh, excellent. I just had a quick questions concerning the inference in this low-dimensional space. So where you basically do an PCA on the space that's discovered by the stochastic gradient descent. Do you have any intuition for why the random subspace performs almost as well as the PCA subspace, at least for the point prediction?
Yeah, let's open that up. So I suppose the reason is that in this subspace, there still is, a reasonable amount of functional variability. Otherwise, we would be getting the same answer as SGD training. PCA, the idea behind the PCA approach is that by trying to construct a subspace that has variability in the parameters, we'll have sort of a proxy for variability with the functions. And we do benefit from that a bit. But it seems like there's still a reasonable amount of variability in the random subspace. And so that could be why. Although we did notice in the figures that the uncertainty representation is much better in the PCA subspace than in the random subspace. So even though we're not seeing maybe a huge difference in accuracy, it seems like the epistemic uncertainty does benefit a lot in the PCA subspace. And maybe part of the problem is just where we're querying our predictive distribution. So maybe we're not actually making test predictions where we'll see a big benefit in better epistemic uncertainty representation. So if we were making predictions far away from the data, perhaps the PCA would look better. But I would say, yeah, it's an interesting question. I think that the answer must be that there's enough functional variability in the random subspace to still help a lot with accuracy. But the differences between the random and PCA subspace are significant enough still such that the PCA subspace is helping a lot with the epistemic uncertainty representation in our predictive distribution far away from the data points. And perhaps on this CFAR example, we're just not really predicting far enough away from our data points.
Okay, thank you.
Okay, so I think we have one anonymous question that I'll ask, and then we're going to go to Freddie, Guillermo, and then Yannick.
Sounds
So
good.
the anonymous question, I believe this was referring back to the swag slides. Why is the training time equivalent to training of classical DL models, and why is the test time greater?
All right. So the training time is equivalent because basically we're still just running the same number. We're basically running SGD with the same number of epochs that we would use for standard training. The only thing different that we're doing is we're computing an average of the iterates after a certain point and computing a low rank plus diagonal approximation to the covariance matrix. So these take essentially sort of a trivial amount of compute to form. The testing time is slower because rather than using a single model, we're now using J models to make our predictions. So we have to do J forward passes through our neural network. And so this might be an interesting open sort of problem right now in Bayesian deep learning. How do we make the test time predictions a lot faster? I think there is a lot of people focused on sort of improving test time scalability. I would say in research papers, this isn't usually a serious question because we're mostly worried about train time when we're thinking about ImageNet and CFAR, et cetera. But maybe in the real world, especially in online applications and so on, it can be important also to have very fast test time. And so if we're carrying around J models, we're going to be J times slower at test time. But the training time is the same. And also, maybe I'll use this as another opportunity to plug SWA a little bit. So this is actually a very, very simple procedure, this idea that where we just basically modify the learning rate schedule and then do an equal average. And it can also be applied to pre-trained models. So if you've already trained your model and don't want to train it again, if you just increase the learning rate, run maybe 10 to 15 epochs and do an equal average, you'll often achieve much better generalization and also somewhat better calibration. And so I'd really encourage you to kind of try it out, in your next paper. Instead of SGD, just try SWA. You will see better performance without additional compute. I would sort of compare it to something almost like batch norm, where it's sort of something you can do that will be quite generally helpful. And we found this not just for computer vision problems, but for quite a wide range of different procedures.
It's actually a really good lead in now to Freddie's question. You can unmute yourself.
Yeah, I don't know how to unmute myself. Thanks. Okay. Hey there. Hi, and very good talk. Thanks for giving it. So my question is purely technical. Back to the stochastic weight averaging, and typically as a deep learning practitioner, I usually use Adam. So it's not pure stochastic gradient descent. Does anything fancier than SGD break the benefits coming from SWA?
I'm so glad you asked. It's almost a planted question. No, yeah, you can benefit a lot from this using Atom as well. So we wrote a blog post on the PyTorch blog, and some of the results there. I mean, part of the point of the blog post was to show how generally applicable SWA is as a procedure, and some of the problems, especially when we're thinking about reinforcement learning, did an SWA-like procedure with Atom. So the basic idea can be combined with essentially any optimizer, and we see similar types of gains. And so I would say in practice these days, we're actually doing it more with Atom than with SGD. And it does still seem to help. There's also a paper that came out recently that was, I think, called SAM or something like that. And the idea is to use a Pac-Bayes bound to find flatter solutions. I think it'd be very interesting if they compared with SWA or tried to combine their approach with SWA, because this is a very, very simple way of finding a flat solution. And we found this to be particularly interesting in contexts like where maybe you're doing quantization. So if you're storing your weights in a lower number of bits, if you're in a flat region of the loss, that shouldn't really matter anymore. If you imagine having this quantized grid, if we shift a little bit, we still basically have a good solution. And so we found that when we use something like SWA, we could actually go down to 8 bits and achieve the same level of performance as standard training.
Thanks. So can you just repeat the name of the paper? Because I lost you there for a second.
Sure. So the paper is SWA. It's at the bottom of this slide. Averaging weights leads to wider optima and better generalization. And SWAG is sort of a Bayesian extension of SWA, a simple baseline for Bayesian uncertainty in deep learning.
Sorry, I thought you meant a paper specifically for Atom.
Oh, sorry, it's not a paper. That's a blog post. But
okay.
Yeah, if you just actually, if you look at the PyTorch Twitter or my Twitter, it'll be a link will be there. I can also send it by email or something.
Okay, I'll find it. No worries.
Yeah.
Thanks.
Yep. Thanks.
Thank you, Freddie. So Guillermo, if you are still here, yes, you should be able to ask your question.
Yeah. So I was interested in the question of like the observation that as you make the networks wider, the generalization seems to improve, and I was wondering if that could be connected to some observations that have been made, some papers saying that, for instance, maybe ResNets are analogous in some way to ensembles of smaller networks or something. So I was thinking if there could be some analogy between ensembles of networks and bigger networks in some way.
Yeah, I mean, it's an interesting question. So I guess ensembling does seem to work no matter how big our network is. And I guess it's something that can be parallelized up until a point as well. I would say after about 10 independently trained models, we start to see only very marginal gains from adding more. So practically speaking, doing ensembling with a fixed size model in many cases will be preferable to just building a bigger model if we're trying to control, accuracy versus runtime trade-offs or something like this. I think it's not clear whether a bigger model could capture an ensemble or whether a single neural net could capture an ensemble of neural nets. I mean, this is an interesting question. I think that a case in which Bayesian methods might be actually problematic is if there is misspecification in the sense that we don't contain anything like a good solution in our support. Now, I don't think this is very much of a risk in Bayesian deep learning because these deep neural networks are hugely flexible. But if it was the case, then we might see weird artifacts. Like we might actually see performance decreasing with increased data size and stuff like this. The reason being that, like, let's consider a simple example where maybe we're considering data generated by a bimodal distribution and we want to do density estimation and we specify just a single Gaussian and we put a distribution over the parameters and follow a Bayesian approach. In a sense, the Bayesian model average is able to capture the two different clusters. But because the model is misspecified, it eventually will sort of collapse onto this, this representation that provides very poor performance, which might be kind of in between the two modes. The sample mean will be the sort of maximum likelihood sort of estimator there. And so that might be the problem is basically that the ground truth isn't really contained in the support of the model. And there was an interesting paper by Tom, not even a paper, like a 2-page note by Tom Minka called Bayesian model averaging is not model combination. And he describes this difference actually quite succinctly and effectively, where he's addressing a paper by Pedro Domingos, which suggests that Bayesian model averaging might be fundamentally flawed because compared to ensemble methods, it appeared to be performing worse as we got more and more data. And Minka points out that although the Bayesian model average looks kind of superficially like model combination or ensembling, it sort of has very different assumptions. The assumption is that one of the models corresponding to one of the settings of the parameters is kind of the correct model, the correct hypothesis. And the reason we're averaging is because of a statistical inability to distinguish between different hypotheses given limited information. And so if it's the case that a combination model, a combination of these hypotheses, like an ensemble of two neural nets or whatever it might be, is actually the correct solution, and that combination is not captured in the support of our approach, then actually Bayesian model averaging might lead to the wrong answers. So your question actually touches on an important point. Like if it's the case that Bayesian neural nets do not contain something close to the ground truth support or close to the type of model that we would want to be using ideally to solve a given problem, then we could see kind of issues in doing marginalization. However, it's my contention that the support of a neural net is very, very large in practice, especially modern neural nets, so that this won't really be too much of an issue.
Oh, thank you. That's quite an interesting answer. Actually, can I ask a related question as follow-up?
Sure.
So yeah, I was wondering, like, also in the papers about NNGPs and the going to the infinite width limit, they say that this NNGP can be seen as training the last layer effectively, and leaving the other ones at initialization. Is there any work doing some deep ensembles or something where it's only done over the last layer? Like, if that makes sense.
Like kind of like first training a model and then retraining the last layer a bunch of times and ensembling.
Yeah, something like that, or even just initializing the model at just keeping the weights random for all of the layers except the last one, and then training only the last layer like n times, and because at that point, I mean, it's basically just a Gaussian process. Now you can just make some sort of Gaussian posterior over the last layer weights or something.
Yeah, that's actually an interesting idea. I'm not really aware of someone that has done that. We have a work in submission which does something a bit like that for covariate shift. So the idea is you kind of train a neural net, use that to create a kernel method, and then adapt your kind of posterior based on some new data set or something like that, if you're considering kind of domain adaptation. And the intuition is that basically the kernel method is solving essentially a convex problem, and so it can adapt to new data more naturally than maybe just retraining the neural net or the last layer of the neural net, because you might get kind of stuck in a local optima. So I think this is kind of a subtle distinction, but people often say, well, actually non-convexity isn't so much of an issue with neural nets because we found that we can just retrain the model with different initializations and find similarly good solutions. But which is, I mean, in practice seems to be true. But if we train a model and then expose it to a new data set from a different distribution, but it's a related distribution, and we want to update the weights, we're already kind of stuck in a local optima. So updating it from that point can be kind of challenging. Whereas if we train a model and then create a kernel from that model, kind of like a finite sort of neural tangent kernel, and then update the model from that in a sort of in the convex kind of way, using a Gaussian process, we can actually do quite well on these covariate shift problems. So it's a slightly sort of related idea that we've been exploring that's kind of in submission. But I think, the idea of just like freezing the other weights and retraining the last layer a bunch of times is pretty interesting. I'd be kind of curious to see how well that does. I think it's certainly an experiment worth trying. Yeah, I mean, it's an interesting idea. I don't know if it will do, I mean, my guess is there'll be much less of a gain per sort of additional model than in regular deep ensembles, but it's also much, much cheaper to get a new model. And so in terms of, runtime accuracy, et cetera, it might actually be preferable to deep ensembles.
Thanks.
Mm-hmm.
So let's go to Yannick.
Hello, everybody. Thanks for the talk, Andrew. Minak has kind of started leading us down this rabbit hole, but I thought your answer was really helpful or interesting. So I would like to ask another question concerning, Bayesian model selection or model averaging. I mean, what are your thoughts on cross-validation for model selection? It's fundamentally not Bayesian, but marginal likelihood has obvious shortcomings. So do you think that eventually we will no longer need cross-validation maybe, or is there a fundamental place for these sorts of techniques? And is there a framework that integrates them in a way that makes everybody happy?
That's a good question. So I'm a big fan of marginal likelihood. And I really like the Occam-Razor arguments in David Mackay's information theory book. And I think it's an interesting mechanism for learning things like symmetries. And for example, Mark Vanderwilk and collaborators had an interesting paper using GP marginal likelihood for discovering symmetries. This idea that, regular maximum likelihood won't select for constraints, but things like marginal likelihood might. They sort of embrace the notion of Occam's razor, which would be in favor of discovering invariances. I think the challenge in today's world is that computing a good approximation to the Bayesian marginal likelihood is very difficult. So we did it for this rethinking generalization paper, and the approximation I think was sufficiently accurate to capture the idea that the model really hates the noisy data set compared to the regular CFAR10. But in terms of like using it as an objective to learn important parameters and so on, I think we're still a long way away, unfortunately. I was sort of disappointed to discover this because I wanted the opposite to be true. And in a lot of the older works that I'd read about Bayesian neural nets by Mackay and so on, they seem to be really promoting the marginal likelihood as a mechanism for model selection, et cetera. But to be honest, I think even if you wanted to learn that alpha parameter, if you're setting your distribution over weights as n0 alpha I using marginal likelihood, you'd have to try pretty hard to find something reasonable. I was sort of shocked to find this out, but with modern neural nets, it's not easy. So cross-validation is actually, right now, a much more practical procedure for learning some of these parameters. And I'm sort of sad to say this, but I think that maybe this also means that this is an interesting research direction, because in principle, I think the marginal likelihood is a lot more appealing than standard approaches to cross-validation. And if we can come up with a good approximation, this does provide a great opportunity to think about model selection and maybe think about things like symmetry discovery using a Bayesian marginal likelihood, as opposed to the approach that I presented very briefly at the end of my talk, which I think is practical, but is also limited in ways that a marginal likelihood might not be. For example, if the data set were noisy or something like that, such that the loss surface was really non-flat, for augmentations which we did want to capture, or symmetries that we did want to capture, then the marginal likelihood, I think, could be quite useful. There are some papers by Chris Holmes's group and others basically equating leave one out cross-validation with the marginal likelihood in certain instances. I mean, I think these equivalences are quite interesting. But I'm sort of the mind that if we can come up with a good approximation of the marginal likelihood, I would be quite happy to say goodbye to cross-validation. And I think that papers like Minka's automatic selection of dimensionality in probabilistic PCA provide very compelling examples of wanting to do this. So the idea there is he basically treats probabilistic PCA as a probabilistic generative model for our data, and there's this parameter we want to do inference over, the dimensionality of the linear projection, and we can compute the approximate marginal likelihood to try to infer this dimensionality. And in most of his examples, it works much better than cross-validation without needing a lot of messy design decisions to make the cross-validation actually work well. So I guess the short answer is, I think right now cross-validation is very practically important, but I think marginal likelihood in general, even though there are some equivalencies with cross-validation, is more principled and potentially a lot more powerful for learning a lot of hyperparameters that would be difficult to learn using other approaches. And maybe deep kernel learning is kind of an example of that. There, we're learning all the parameters of the neural net through the marginal likelihood of the Gaussian process, and finding that we can achieve better performance than standalone neural nets. And this is kind of a type of kernel learning that wouldn't otherwise be very possible. I mean, people often talk about the benefits of GPs as being the function space representation and the principled representation of uncertainty. And I think those are definitely benefits, but practically speaking, maybe the biggest benefit is this marginal likelihood, which gives us a simple probabilistic objective for kernel learning, which isn't available to alternatives like support vector machines or other sorts of kernel machines. And I think this has brought kernel learning to a whole new level, where instead of just considering a kind of modest additive composition of RBF kernels with different bandwidths, we're actually now looking at projects like the automatic statistician or spectral mixture kernels or deep kernel learning, etc.
Thank you, Yannick. With regard to the last question, Claire brought up Bayesian deep ensembles via the neural tangent kernel. Claire, would you like to expand on that?
Oh yeah, I was just saying, related to the idea of sort of trying to use like the infinite width limit to come up with ensembles, there's some interesting work out of the OXCSML group this summer that was sort of doing something kind of similar. Not exactly what Guillermo was suggesting, but might be interesting.
So what's the idea?
So basically you sort of tweak the way that you run SGD to add a bit of extra noise so that the sort of limiting covariance, the covariance kernel of your limiting solution ends up looking like the neural tangent kernel. So then you can sort of get like the samples that you get from different initializations of your network end up looking like the posterior of this NTKGP.
Yeah, that sounds really cool. I have sort of a meta thought about neural tangent kernels. This is something I get asked about a lot. So I love Gaussian processes, and I hope that they continue being widely applied. And I think there are a lot of exciting research directions for these models. But I kind of worry that there's sort of a misleading claim that's evolving, maybe implicitly, that Gaussian processes are basically just neural nets, because if we look at infinite width Bayesian neural nets, we get a Gaussian process. Same kind of thing. We don't even need neural nets. Let's just use Gaussian processes. Maybe there will be a time where we don't need neural nets, but in practice, these are often very different models. A lot happens when we take infinite limits, and there's a reason we're not using infinite limit BNNs instead of regular Bayesian neural nets, or deep neural nets instead of Gaussian processes for a lot of problems right now. And that's because, for instance, when we train a regular neural net, we learn all the parameters in a regular neural net. We are doing a pretty non-trivial type of metric learning. We're learning a similarity metric, which, given a finite data sample, provides a pretty good description in many cases of the problem we're trying to solve. So we have an example in the deep kernel learning paper where we have these what are called Olivetti faces, where you have faces which are rotated by different orientation angles. And the goal is to predict the orientation angle of a given input face. Now, a standard kernel method, like an RBF kernel, will say that two faces or two images are similar if the Euclidean distances of the pixel intensities are similar. And of course, we know this is going to be a horrible metric for trying to solve this problem. Maybe in the limit of infinite data, we still have a universal approximator. We're just doing interpolation. And so that'll be all right. But given a finite data sample, we want to learn something different. We want to learn a kernel function that says these two faces are similar if they have similar orientation angles, and that will help us generalize and solve our problem effectively. And I would say in practice, that's the kind of thing that a neural network is doing. That's really what representation learning is all about. And that's not something we're getting with these neural tangent kernels and these infinite width Bayesian neural nets. We're getting fixed covariance functions. And so I think there's kind of a danger in sort of like maybe being overly enthusiastic about how neural nets are sort of special cases of Gaussian processes or something like that. There are actually pretty meaningful differences between these models, and maybe bridging this gap is an interesting direction. I think kernel learning is a way to sort of bridge the gap, but neural tangent kernels as they stand right now, I think are fairly different from standard deep neural networks in the way that they try to do representation learning.
Well, actually, I have maybe a little follow-up question to that. So when we get into this like topic of generalization and invariances and things like that, I'm just wondering, what role do you think that, let's say, causal inference is going to play in this? And do you see a role for Bayesian deep learning in the causal inference literature, let's say?
Yeah, so I think there is a connection between, learning invariances and causality and things like this. We're sort of trying to discover something a little bit more fundamental about our problem that wouldn't be signaled by standard maximum likelihood, et cetera. I mean, I think it's kind of crazy that we use maximum likelihood to train a lot of models. We sort of have a somewhat broken procedure combined with a broken model in some way, and we get something that's sort of okay in some instances. But if we think about it critically, maximum likelihood doesn't really make sense. Like, I mean, there's all sorts of examples that can easily break maximum likelihood. Like if we have even a mixture of two Gaussians, right? Like, and we collapse one of the components onto a single point, we're going to achieve infinite likelihood, but we're going to get a model that certainly doesn't generalize. And I don't think the answer is just reinitializing our model a bunch of times and hoping that we get trapped in a local optima that doesn't correspond to that infinite likelihood solution. And that is often, what we do in practice. And so, I think that going beyond that and trying to discover something a bit more fundamental about our problems that has semantic structure is really important. I would have a similar feeling about things like shortcut learning. So there's an interesting paper that appeared recently showing that there were a lot of machine learning methods that were achieving good performance on certain tasks, but by doing almost what we really wouldn't want them to do, like sort of learning that maybe all pictures of car have a blue sky in the background. So if there's a blue pixel, it's a car, etc. In a sense, I wouldn't hold this too much against the model. Like, given the data set and the way the learning objective is specified, that's a fine way to solve the problem. We haven't given it information that would allow it to realize otherwise. And so in a sense, this is sort of expected, but also at the same time, we want to do better, because if there's some kind of covariate shift or something else, then we're really going to be in trouble if we're doing this shortcut learning. I think learning invariances is maybe part of the solution, but not entirely the solution, because part of the issue is just the information that we're giving these models and the learning objectives are not really calibrated to kind of generalization in a deeper way, in a way that sort of recognizes semantic structure, which is sort of important for solving many of these problems more broadly. I think invariance is part of it, but it's not entirely the answer. I mean, I would relate it more to trying to find a compact representation of the data. And I would think this is, in general, a little bit away from things like shortcut learning, but not necessarily. Like maybe learning that there's a single blue pixel in the image is a great way to find a compressed model which achieves great generalization on that problem, but is like completely not aligned with finding a good sort of semantic understanding of the problem. And so I think they're related, but they're also a bit different. I think that probabilistic approaches to deep learning are connected with causal inference, in the sense that sort of probabilistic graphical models and things like this are connected with causal inference. So understanding conditional independencies and things like this can give us a better sort of causal understanding of the relationships between different variables. I'm pretty excited to see where this leads. I think being able to do things like come up with better approximations to the marginal likelihood might be important in this context. And maybe that's an interesting and presently fairly unresolved question in Bayesian deep learning. I mean, we're currently basically seeing that we can do approximate Bayesian marginalization with tempering or not, whatever. I don't think that really is a major concern or too related to whether we should be doing Bayesian deep learning or not. Achieves better generalization than classical training. And so that's sort of a big step forward and potentially a reason that people should be doing this instead of classical training. I mean, if you get the same training time and better performance, why not? But no one is actually using the marginal likelihood, as far as I can tell, to do anything. And I think it would be very interesting to sort of use this for model comparison, model selection, neural architecture search, for discovering something that might have a more meaningful semantic representation or something like this. So I think there is a role to play, but maybe this is an unanswered question in that direction.
Thank you very much for your thoughts. Before we go back to Freddie, can we go to Yunsu? Yunsu, I think you can go ahead.
Hello, can you hear me?
I hear you.
Okay. Thank you for a great talk. And you kind of mentioned about depths of neural networks makes it kind of more interesting and kind of different from other models. May I ask what your intuition is on the depths of it? Would the depths lead to the better priors for our problems, or is there another reason why you would say depths makes neural network more interesting from the others?
Right. I mean, when I give my course on Bayesian ML, I have a small unit on Bayesian neural nets and deep learning more generally. And I think one of the most salient questions is, why do we care about depth? I mean, that's really what defines deep learning. We have these deep hierarchical models. And I think there's a lot of confusion on this point. It's often conflated with flexibility, but we already know that if we can build a very, very wide neural network, we can get as much flexibility as we would ever want. And perhaps that's the reason it took so long, aside from computational constraints, for deep learning to be very seriously explored. Why would we care if we can achieve the same flexibility with a lot of width? And if we have kernel methods, later on, that do give us universal approximation, etc. So the real practical benefit of depth has to be related to inductive biases rather than flexibility. We know that we can apply a GP with an RBF kernel to CFAR10. Might do all right, but it'll certainly not do nearly as well as a convolutional neural net, which has many layers. And so the depth, I think, is sort of giving us interesting inductive biases. It is giving us a hierarchical representation of data. It's helping us find solutions which will generalize better because of those inductive biases. And this is not something that, interestingly, is being explored that much recently. It was sort of interest more in 2012 or so, when people started to realize that deep neural nets could achieve very good empirical performance. But I think potentially out of convenience, we started to focus more on width again, like NTKs taking infinite width limits, etc. I actually don't think it's really width that is interesting with these models, it's depth. And the depth does give us inductive biases, such that if we view this from that diagram, which is partly inspired by Mackay's work in thinking about Occam's razor for model selection, and these similar diagrams that he sort of represented for reasoning about those problems, we would sort of expect that the depth sort of allows us to distribute our mass in a way that is aligned with a lot of these problems that we're trying to solve. The next question is, well, is there an ideal depth? Like, I think maybe, philosophically speaking, we might want infinite width, but I don't think we would necessarily want infinite depth. So there was a paper by David Duveneau and collaborators about pathologies of deep networks, and they were focusing, I think, mostly on deep GPs. And they showed that basically the induced distribution over functions, when you had a lot of depth, could be kind of pathological. And this sort of then leads to the question of, well, could we do inference over this parameter? Like, I don't think we would necessarily want infinite depth. We might want infinite width. And I just noticed, I haven't read the paper, but I have Twitter, and I saw that there was an interesting paper out of the Cambridge group with Miguel and others reasoning about how to do inference over the width in a neural net. And that, to me, at a high level, seems like an interesting direction.
Thank you very much.
Excellent. So I think if Freddie is still here, he has another question, and I think that's going to have to be the last question for today.
Sounds good.
Hey, okay, last question.
Hello.
If we go back to using multi-layer perceptrons, deep ones on MNIST, do you think there will be any paths, parameter paths waiting to be discovered? And would they be somehow connected to some type of symmetry like translation equivariance?
That's a great question. So there was an interesting archive paper by Ben and Nejabur, which was about whether we could just discover a convolutional neural net. And he showed, I think, that we could get about 85% accuracy on CFAR10 using a fully connected net with a lasso-like regularizer connected to things like minimum description length, and that this would capture some properties potentially of something like a convolutional neural net. So I think in principle, we probably don't want a convolutional neural net. We just want something a bit like it. And from a Bayesian perspective, this might amount to using something like a fully connected net and then having a distribution over the parameters, which is, say, like a Gaussian distribution that has zero mean and high variance where we have the convolutional connections and low variance where we have other connections. And this means that we would have our distribution over architectures kind of concentrated around something like a ConvNet, but would allow for other possibilities. And we would want to fine tune and move a little bit away from the ConvNet, typically for most problems, because we might not want exactly translation equivariance, et cetera. I thought the intro of Benham's paper was kind of nicely written in the sense that it's like, well, a lot of the story of deep learning is about discovering features rather than handcrafting things. They discovered, for example, that ConvNets were learning something in early layers like Gabor features, but if we just use those features directly, it won't work as well as a ConvNet because, of course, they're doing something a little bit different at the same time. They're learning something else. And so I think that's philosophically appealing. I think the practical challenge is part of the reason that ConvNets can be very deep is because of the sparsity. It's just sort of practically impossible to build an interesting, fully connected neural net like a convolutional neural net. Like, so if you have an image with 1,000 pixels and then we have 1,000 hidden units, we already have 1 million connections and not a very interesting model. And so I think just computationally kind of building fully connected nets that will allow us to realize this intuition will be very difficult. Potentially something kind of in the middle could be inspired by some of these group theoretic representations. So, Taco Cohen and Max Welling have been doing a lot of work in this area. We had a paper that I briefly mentioned about building ConvNets, which are equivariant to Lie groups. And one interesting thing we noticed is this sort of trivial Lie-conv model in that paper actually performed really well. And it didn't capture a lot of the invariances that a convolutional neural net would capture. So we considered sort of different versions of Lie-conv invariant to different symmetry groups. And this trivial model, while it contains the sparsity of something like a ConvNet, it actually is a lot more general. And so maybe something like that could be an interesting starting point for following something like a Bayesian approach, where we have a distribution over parameters and we sort of concentrate around something that might represent some kind of invariance, but also allows us to deviate from it and discover what sort of interesting invariances might be in the data. This Augarino approach is kind of interesting in the sense that, and maybe distinctive in the sense that it can be applied to basically any architecture and any loss function, so any kind of maximum likelihood type thing, and does seem to pretty reliably discover the right level of invariance in the data by discovering kind of the right amount of augmentation. I guess that the intuition is that if we want, for example, a model that's rotation invariant, then we can just take whatever function we started working with and create a new function, which is the average of that function applied to all sorts of different perturbations of our given input under some transformation. And then we just want to learn the parameters of this transformation. And interestingly, the loss surface is very flat up to the maximum level of invariance. So we can learn things like partial invariances and stuff. Where this will probably break down a bit is when we have things like noisy data sets or sort of situations in which there is more of like a gradual increase in the loss as we apply these helpful transformations, and we want to learn them using something like minimum description length. And so I don't know, so I guess in short, like I think this is something we can try to learn. like, discover a convnet from scratch or whatever, but I think it'll be hard doing it just for computational reasons, starting
Sure.
from something like a fully connected net. I think there's also an interesting related problem. Like I think a lot of theory, both in Bayesian and sort of non-Bayesian learning around generalization, is pretty myopically focused on this question of support, like how flexible is the model? A model is misspecified if it doesn't contain the ground truth in the support. Whereas I think of misspecification a little bit differently. It's sort of, always misspecified, and the extent of misspecification relates to how the distribution of support differs from what we would like ideally. And I think where this actually could really have a meaningful difference is if we're considering a model like a huge, maybe fully connected neural net, and then we have like a distribution over our parameters that is zero mean and high variance for, say, convolutional connections, and very low variance, epsilon variance for everything else. I think from the perspective of a lot of standard generalization theory, that model would be no different from the original fully connected net. But in terms of actual generalization, it would be exactly like the convolutional neural net. So I think this is, an interesting direction. Maybe it's
Definitely, yeah. I mean, I wouldn't suggest going back to MLPs and trying to discover CNNs, but it does beg the question: if we think of current CNNs as a known MLP, what else is out there waiting to be discovered? Maybe we should take this pathfinding a bit more seriously and kind of try to discover interesting symmetries.
I agree. Yeah, I think that's a really exciting direction.
Thanks.
Thanks.
Okay, great. Well, thank you again, Andrew, for your presentation and discussion, and really thank you to everybody who joined today. We had a great turnout and some really good questions.
Thanks so much. It was great to be here.
Awesome.
Thank you.
Thanks. See you later.
Bye.
Bye-bye.